Hi, my name is Michael de Podesta, and this is a short talk it's really about net zero. I've been trying to get my ideas clear on net zero. When I've talked to people, there seems to be such a lot of confusion about the idea. I thought I would try and write down something about net zero. So let's start with how we know the Earth's temperature is warming. Now, there's actually lots and lots of ways we know the Earth's temperature is warming. It's not obvious in any one particular place because it's about the whole globe. And one of the most powerful ways we know the Earth's temperature is warming is we have lots of weather stations. And the data from these is monitored. This is about 30,000 currently. Historically, there were not so many, but about 30,000 now. And each dot on this map represents a weather station, and typically it's taking data every 10 minutes. So these data are first checked. There are lots and lots of ways they can be in error. They're first checked and then averaged to produce daily, weekly, monthly, yearly and decadal averages of the temperature. And we can see, we look at each station to see whether the record from that station has changed. That's called the anomaly. The climate anomaly, and we look at the anomalies of all the weather stations around the world, and when we put them together we get the global temperature anomaly. So this scale here is the global temperature anomaly. Here's 0 and here's 1 degree Celsius, 2 degrees Celsius, and each dot on here represents an analysis of all the temperature measurements from meteorological stations around the world in that year. So there's one per year, and the grey bars here represents the statistical uncertainty associated with that measurement. So here's 0, and this is the average of the readings between 1850 and 1900. So we're measuring changes from that, and you can see basically the temperature went flat for a while, and then since the 1960s, basically 60s or 70s, it's had this very striking dependence on it. So you may remember that last year was the hottest year in many years, but it's not this particular anomaly that's significant. It's worrying, but it's not the really worrying thing. There have been anomalous years back in history. What's really worrying is this trend. This trend is pretty well established, and it's very, very frightening in itself without worrying about sudden changes. And what this talk is about is that this dotted line here, the dotted line down here is the trend of existing data, but up here it's an extrapolation. It's the future. It's not yet happened. And we can make something different happen if we do something different, if we change business as usual. And in particular, we can make this line stop going up and stop rising. We've got no way to make it go down, but we can still stop it rising. And the way to do that is to put net zero emissions of carbon dioxide into the atmosphere. And that's the only way we know to stop global warming. Okay, so how do we know that the warming is caused by anthropogenic emissions of carbon dioxide? I can't actually be bothered to tell you the answer. The reason is I've given this answer so many times. There's so many, it's just part of a basic understanding. And if you've got to use your QR code on this, you can, or go to my blog, you can find talks that I've given about that. But I thought I would say just how long we have known about the effect. And it's a very, very long time. So if we come back to this graph here and we put on here in 1857, so the 1857, not 1957, 1857, John Tyndall in London discovered that air absorbed infrared radiation. And when he investigated this, because he was astonished, he thought that infrared radiation would go straight through, just like visible light goes straight through air. But he was astonished to find that the infrared radiation was absorbed by air, and then when he investigated, he found it was just the water vapor and the carbon dioxide in the air that was doing the absorbing. It wasn't the 99% of the oxygen and the nitrogen. He was astounded and immediately realized its significance for the way heat travels through the atmosphere. Back in 1898, Svante Arrhenius was very concerned about ice ages. People didn't know the cause of ice ages back then, and one of the speculations was that it could have been about a change in the level of carbon dioxide in the atmosphere. And he made a calculation, an absolutely brilliant calculation. I've been meaning to write about it for a while. But if we ever managed to double the concentration of carbon dioxide in the atmosphere, then the Earth would warm by about 4 degrees Celsius. So he thought this might be a possible explanation for what had happened in ice ages. But and he was aware of carbon dioxide emissions from burning coal, but it was just a few billion tons a year at that time, and it's not really significant. In 1937, Guy Callender, again an absolute genius, British scientist working alone, he said that our emissions of carbon dioxide have already warmed the Earth. He detected this warming here just by looking up data from books in the library. Absolute genius. But he wasn't concerned about it at all, because at that time we were emitting less than 5 billion tons a year of carbon dioxide into the atmosphere, and he thought it would make a little mild warming, and he was very happy about that. So I could go on through these intervening years. So through these intervening years, this effect, this global warming effect, was known as the Callender effect. But if we fast forward to 1981, and now emissions had risen quite a lot, and what the rate of rise was very significant. So we'll be in big trouble if we don't reduce carbon dioxide emissions urgently. And back in 1981, which if you remember is a long time ago, he wrote a paper and predicted what would happen. So here's the dates: 1950, 2000, 2020. And he made a worst case scenario, which was this one, and a best case scenario. This one assumed that we took action immediately to stop the emission of carbon dioxide. The pink line shows what's happened since. So basically, what has happened is worse. The temperature rise has been worse than Hansen's worst case scenario. And so it's very impressive when someone predicts something 40 years out. Back here, there was no warming to speak of. Things were at the temperature trend when he wrote his paper was actually slightly down for the previous few years. So this is enormously impressive and makes it clear just how strongly carbon dioxide is involved in this warming. And if we had taken notice of that at this point, if we tried to do everything, the Earth would now be a 0.5 degree cooler than it is at the moment. Okay, so here we are. This is the anomaly. This is what's happening. So we can summarize that. The world is warming at about 0.2 degrees Celsius per decade, which means that children born now, as they reach 25, the Earth will be a 0.5 degree warmer. Later on in the talk, I'll try to convey to you how insanely fast this changes. A change in the temperature of the Earth's surface is astonishing. The only way we know to stop that is net zero. It's the only way we can stop global warming. So if you meet someone and they say, oh, this net zero nonsense, and they go on about it as if it's some political choice, please tell them it's physics. And if they are against net zero, they are pro global warming. And ask them just how hot they would like the Earth to get. Because if we don't reach net zero, the Earth will just keep warming indefinitely. Okay, so let's look at the path to net zero. How do we get there? So here is the emissions of carbon dioxide in billions of tons. I won't, so currently I think we're at 36 billion tons up here. And there are about 8 billion people on Earth. So this is more than 4 tons per person. And this line here shows, you can see the emissions have risen every year, or practically every year. The trend is very clear since the 1950s. So this was when Callender was doing his calculations, and he saw emissions down here and very little global warming. 1980s, Hansen was here, and he had seen this rise and feared exactly what was going to happen. But so let's just zoom in on this bit here. And here's business as usual, this rising trend. And what I'm going to suggest to you, and I'll give you some evidence for it later, is that we are close to peak carbon dioxide emissions. I pray that it's true. There's some weak evidence that we might be close to it, that I might see it in my lifetime. And what we've got to do is get to zero carbon dioxide emissions. So let's imagine that one route to that is here. We just cut all the carbon dioxide emissions right now. That's kind of inconceivable. Would probably not be, would definitely not be popular. It's probably not achievable in any way. Here's a sort of plausible plan that we just cut emissions linearly down to 2060. Or here's one that we take a longer time to do it. And let's just label those A, B, and C. And let's see what that would do to global temperatures. So remember this graph, here we go. And here's that graph again. So here's the global temperatures. And if we chose option A, then basically temperatures would more or less stabilize. You'll see here it comes a bit below 1.5 degrees, probably not quite achievable, but that's indicative A. And then here's B. You can see we've emitted more carbon dioxide, so we get more warming. And here's C. We've emitted more carbon dioxide and we get more warming. So the key thing I'd like you to understand from this, it's not been specifically calculated, those are just indicative, that the longer we take reducing emissions, the warmer the Earth will get in the meantime. And even after we reach net zero, the Earth won't cool. So as hot as we make the Earth, that's what we've got to deal with. So here's a sort of realistic pathways that people have calculated, talking about to reach limit warming to 1.5 degrees. So this was in 2021, I think. And so we would have had to have cut emissions already by quite a lot, which has not happened globally. But these options are still on the table, 2 degrees. So just to say that if we want to limit things to 2 degrees, we're currently emitting 36 billion tons a year. We could do that for 40 years and then we'd have to stop immediately. That's the budget that will take us to 2 degrees Celsius. So we could come out from 2020 up to 2060 and that amount would warm the Earth. So this is a more reasonable path to getting to 2 degrees Celsius. And you can look at more details of these projections. So this is a paper called When Warming Ends, When the Carbon Pollution Stops by Michael Mann. Here's the link and here's a QR code to it. And it looks at what happens to emissions and carbon dioxide concentrations in the atmosphere and temperature. Now, I just want to say a bit about the net bit of net zero. So here's this diagram again. So let's just try to be a bit realistic. And option A is not realistic. And options B and C are not realistic either because they go to zero directly. They imply that the way we live our lives at the minute, we can go directly to zero emissions. We just can't do that. This bottom bit, we can't do. Everything will bottom out, even in very optimistic scenarios. There's a gap here, which we don't know how to fill. So that we can't think of a way to reduce emissions to actual zero. So what this bit here is where the net bit of net zero comes in, is we're imagining that by 2050, we will have figured out how to remove some carbon dioxide from the atmosphere. Optimistically, we might conceivably be able to remove perhaps 1 billion tons, 1 billion tons. We're emitting 36 billion tons now. By far the cheapest way to stop putting carbon dioxide in the atmosphere is just to not put it in there in the first place. Taking it out of the atmosphere is expensive. But in order to get to zero, we will need to do that. Now, I will say that if we reach this point, we will have reduced the rate of global warming from about 0.2 degrees per decade to about 0.02 degrees per decade, or 0.2 degrees per century. And so things will not be quite so urgent at this point, as we would feel like we were really on top of the problem. But still, that's a thing we just don't know. But this is where the net comes in, because the net effect of removing carbon dioxide from the atmosphere and reducing carbon dioxide emissions is to reach net zero emissions into the atmosphere. So we don't know how to do the last bit. We don't know how to reduce emissions completely to zero. We still need to invent ways of removing carbon dioxide from the atmosphere to achieve this net zero. Now, is there any reason to believe that any of this could ever conceivably happen? Lots of people tell me it's just not possible. I'm nutty to think about it. So I just trawled for a few graphs to put together. I can't prove it to you, but here's a graph from Ember, and they point out that wind and solar have gone from 100 terawatts to 1,000 terawatts faster than any other source of electricity in history. So here's years, and here's the point at which global generation in terawatt hours. So roughly speaking, the UK uses 1 terawatt hour of electricity per day. So about 300 terawatt hours per year for the UK, roughly. And so globally, wind and solar have gone from 100 terawatt hours. When they pass that point, they've risen incredibly fast. Here you can compare it with the growth of nuclear power and gas and coal. Now, of course, this coal would have happened a very, very long time ago, and the world would not have been quite so. The problems would not have been so big. But nonetheless, it points out that the rate at which solar and wind are scaling is beyond anything that has ever happened in history. This is really significant growth. We're still small, we need to get big, but nonetheless, it's still a phenomenal change, and it's happened very recently in 10 to 15 years. This graph shows the growth in global wind and solar. That means that renewables make up more than 30% of global electricity. That still means that 70% is fossil, but things are changing. So you can see that the biggest contribution to renewable electricity is hydroelectric power, but there's not the scope to grow that because it's expensive, it's slow, and lots of questions about how smart it is to do that. But nonetheless, we're grateful for it now. And here is wind and solar, and you can see that we're up at 30% of global electricity. So if you continue that rise another 10 years, and another 10 years will be another 10%. So it's slower than anyone would like, but it's still phenomenal on any reasonable scale. And here is a graph showing that electricity is getting cleaner, not as fast as anyone would like. This is the carbon intensity of electricity generation. So this is 2000, 2010, 2020. And you see that India is not really doing very much. Russia, not really doing very much. The US, if you follow that through, US is getting cleaner electricity. Look at China. China's come down by 25% in the last 20 years, while still having a vast population and large economic growth. The EU is here, and the UK is similar to that, down at about 200 grams per kilowatt hour. So all over the world, electricity is getting cleaner, and as it gets cleaner, we can use energy and make less damage. And here's one from the UK. Last year was the first year we generated more electricity from renewables than from fossil fuels. And if you look at this graph here, you can see where it's going. We are stopping using fossil fuels. It's slow, but it's hard to imagine it really happening faster, given the difficulty of raising billions of pounds and so on. And here's another one which I think is very significant, and also gives you an idea of how much you're being gaslighted by the press and so on. This is from Bloomberg, and it shows car production. So this is the pink bit here is the future, and you may have heard that EV production has stalled and there's a crisis in EV production. You might be thinking, maybe we're not going to go to EVs after all. Well, we are, because this is the reality that ICE cars, internal combustion engine cars, sales of those peaked in 2017. Sales of those peaked in 2017, and ICE car production has been declining every year since. So the crisis is for conventional automobile manufacturers whose product is disappearing under their feet. Electric cars are growing at, I don't know what it is exactly, it's 10 or 20% every year. It's serious. So lots of stuff is going on. It would all be nice if it had started sooner and happened faster, but things are happening. We could still do better. I just wanted to take a look at what's going to happen. Everyone wants to know what's going to happen. What are the consequences of what we're doing? And of course, it's the future, so we don't know. But what I'd like to do is, so if we look over this timescale from 1850, this goes up to 2050. So these are the lifetimes of the people from my family, and we want to think longer term than that. So let's compress all this into a small part here, and let's take a look. That's our current era. That's the age of basically the Industrial Revolution. And let's look at the past and the future. So if we take a look here, if you squeeze that graph up, it's got a bit going, the temperature's going down a bit, and then it's coming up. And let's go to the past, and we'll see what, that we're going right back to 20,000 years BC. So really long time ago. And you can see that here's the current rise. And you can see that this is incredibly fast compared to the changes that have happened before. So 20,000 years ago, the Earth was about, you can see that's minus 4.3. And then if we compare it to the end of the last ice age, that amounts, so that's 1800. So this is just now. And so that change here, which corresponded to melting ice sheets over vast parts of the Earth, happened in about, so what is that? That's 8,000 years. So let's call it round up to 10,000 years. 5 degrees Celsius in about 10,000 years. So that's about 1 degree Celsius in 2,000 years. That's the rate of change of temperature during the last ice age. At that point, that caused 140 meters of sea level rise. So if you can imagine going to the coast now, and imagine the sea going down 140 meters, 500 feet, that's how that's the level of sea level, and that's how much ice was trapped up at the North Pole. So now if we come to so the population of the Earth at that time was 1 million. So that's like a little bit of West London was spread out over the whole Earth. So as sea level rose, again, it's rising it's 140 meters, but it's still a very slow rise. People would just move inland as the sea level rose. Now, this is the future, so nobody really knows, but this is projecting a 3 degrees Celsius rise in global temperatures. And that's a reasonable guess. It's, I think the renewable energy transformation will take place. I think it's almost inevitable now because it's cheaper and better, but people will slow it down and fight against it. And so as I advocate for the transformation to renewable energy, what am I advocating for? How would I like this graph to change? I'd like it to change like this. That bit could be here. So maybe 1.5 degrees is not quite possible now, but 1.6 would be good, better than 3 degrees. But this is what we're fighting over, the difference between 1.5 degrees and 3 degrees Celsius. Now I will say a little bit just here, so this cooling trend here, and this trend here, this was caused by changes in the motion of the Earth around the sun. And what this does is these are very, very tiny changes. And what it does is it shows you just how sensitive the climate is to tiny changes. And you can see that what we're doing now, when it's not tiny, it's on the same magnitude as caused ice ages, but it's happening much more rapidly than anything in the last 20,000 years, probably in a much longer period than that as well. So we're committed to at least 1.5 degrees Celsius of global warming. Warming by 3 degrees Celsius will likely be catastrophic. Limiting this rise leaves a more habitable world for our children. It's really a thing worth doing. And I've avoided detailing what the catastrophes will be. I don't know what the catastrophes will be, but even just the most basic thing, which is sure to happen, the rise of sea levels, is going to be devastating, because unlike at the last ice age, where people could just move inland a bit, we've built our cities, New York, London, very close to existing sea level because the climate was so stable for so long. And so they're alike. I don't know what the disasters will be, but it's a thing we shouldn't want to push. And so I thought I'd end up with a little cartoon, which is a stroll through the past. And it's from the XKCD website. And it's a timeline of Earth's average temperature over the last 20,000 years. That's the same period we were looking at there. And it's the cartoonist's response to when people say the climate has changed before. This is what they're talking about. The climate has changed before. And so what we've got here is 20,000 BC, 22,000 years ago. And that was how much colder it was than the average 1961 to 1990 average. And one of the things I'd like you to focus on is this line. So this is the average temperature of the Earth at that time. And the temperature changes by typically less than 1 degree Celsius in 1,000 years. Let's take a look at it as we go. So let's just wander through. We're just going to make this thing move through here. And so back then, it says the world is about to warm up. That's because of those small changes in the orientation of the Earth in its orbit. And that's causing this change. So look here, that was 1,500 years. It's changed by a fraction of a degree. So now as the ice sheets start to melt because of that orbital change, what happens is that land becomes free of ice and CO2 levels rise. And the CO2 starts to warm the Earth and we get a runaway effect. So the CO2 is causing extra warming and melting, and then the melt rate speeds up, increases the release of CO2. So look here, we've gone, this is the start of the Ice Age. We've gone now, so this is now 5,000 years, less than 1 degree of temperature rise. So this is when the Lascaux cave paintings were made, coming through. So humans reached North America. So here the sea levels were very low and the ice had retreated a bit and people could cross from Asia into North America. In a little while, the sea levels are going to rise and cut off that route. That's where the Bering Strait is now. So there's still massive ice sheet. Now this is big temperature change. Look, that was about 1 degree in 500 years. So the ice sheets withdraw from Chicago. You get a sense of the magnitude of the changes that have happened. So we have evidence of some human settlements here. Then there's a little bit where temperatures start to decline for a little while, called the Younger Dryas, and then the warming resumes. So human settlements at Jericho, so people living in the Middle East. First development of farming. So before that we were hunter-gatherers. And again, a big rise there. Look, that's 1 degree in about 1,000 years. So rising seas cut off the land bridge between North America and Asia. Cattle domesticated. Temperatures starting to level out. So historically, so this is 8,000 BC, and things were just a little bit warmer than they are now. This is called the Holocene climate optimum. And after that, there's a very slow decline, again, due to the orbital changes. So people, when they analysed this, they thought that the Earth would be slipping into another ice age. As things are, that's not going to be a problem. So just look at this, the magnitude of the changes here. Humans developed copper metalworking, gold metalworking, the invention of the wheel. Wow, astonishing someone can put a date on that. So again, we've got this very, very slow cooling, but just look how stable this is. This is stable to, in 500 years, it's stable to fractions of a degree. So here's the mummification, Indus Valley civilization, earliest human whose name we know, Stonehenge, Great Pyramids, 2,500 BC. Writing developed in Egypt. Here's iron ore developing, iron smelting developing. So again, just look at the stability of this line as we go through these things. Now 500 BC now, and things are going to start to accelerate in terms of what we know, because this is history, and what we had before was prehistory. So here is Jesus' birth, Muhammad's birth, medieval warm period, and then there's a cooling period, the so-called Little Ice Age. Little Ice Age is 0.5 degree in 500 years, and then we come to the present day. So here we are, and here are options A, B, and C that we were looking at before. And just look at the slope of this here. We're changing by more than 1 degree in about 100 years. What is happening now is totally exceptional, and we really don't know what the magnitude of these options are going to be. But the smart thing is to make them as small as possible. So the conclusion here is net zero is the only way we know to stop global warming. And if you're against net zero, that's the same as being in favour of continued global warming. And the longer we take to reach net zero, the warmer the Earth will become in the meanwhile. So limiting this eventual rise leaves a more habitable world for our children. So that's the end of this talk. I hope it made some sense to you. Get in touch if you'd like to discuss anything. Thank you very much.